Welcome to yet another exciting and dynamic video, in this case part 2 of my Information Technology Thoughts series of videos. In this video I'll be discussing the advantages and disadvantages of a distributed computing architecture. Before I continue, let's look at a little bit of history. In the beginning, computing was centralized and resided within a single OS image and often only using a single CPU. It was a simple time, but this model had a major problem. In order to expand your application, you needed to expand the entire computer. This was done, but it was very costly. Most applications during this time had no choice but to be centralized, or at least to reside in a single OS image or a few single OS images, connected with some form of high-speed interconnect, such as multiple LPARs on a mainframe. These remained so, although the solution to resolve the performance issue was initially asymmetrical multiprocessing, and then moved to more advanced versions of this architecture, often called NUMA. However, while the bulk of applications in this early era were centralized, that is, required a single OS image or just a few, some applications did not need to remain centralized. They were often simpler or less mission-critical application. Email is a simple early example. Initially, mainframes and other similar systems provided users email systems which were centralized. But with the advent of the internet, UCP and other similar technologies, email became an early type of distributed applications purely because residing on a big box was very expensive and distributing it was significantly cheaper. The impact of this concept was profound, as moving to a low-cost, although I have to admit less secure architecture, applications which made no commercial sense in the old centralized world suddenly became far more viable and used a lot more. Reducing costs often created new use cases where they never existed before, and as a result, these new cases or use cases exploded. Other early examples of this kind of distributed computing was word processing, spreadsheets, and presentation applications such as PowerPoint. However, apart from email, many of these applications were not really distributed, more so than they were simply isolated. Putting aside these PC-type applications, within many companies, other applications, as a result, became far more prevalent. A good example were CRM systems. These were often less mission-critical than, let's say, a GL or general ledger application. Other examples were ERP systems and a host of satellite applications these applications in turn spawned. Then we came to an entirely new class of a distributed type of application, or an application which was suited to a distributed architecture, and that was data warehousing and, more specifically, business intelligence applications. Now, I have to admit, BIDW really is a can of worms in many ways, and that would take several videos to cover in depth, and I'm certainly not going to drill down into too much detail. But nonetheless, here was an application class which could utilize a distributed computing architecture. This trend continued, and it actually spawned an entirely new type of application, one which relied on an intermediate layer which allowed it to talk directly with other applications, basically utilizing what generally used to be called back in those days a service-oriented architecture. No more do client applications need to connect to a central database. They could now actually talk to other applications in this distributed world. This was an ideal environment for the growth of distributed computing and what has become, in many ways, the public cloud today. I must admit, for those people who are extremely experienced in the IT world, you may say this is an incredibly simple summary of the history of what had occurred. And I have to admit, I've neglected a whole range of additional use cases and directions, such as HPC, which was a critical element in the development of distributed computing, at least the technology, as was the internet, browsers, and even today smartphones and their ubiquitous apps. So just to emphasize, this is very much a high-level view, the so-called marketing 20,000 foot view. Let's drill down into a specific application and how it worked. I'm going to use a simplified versions of one of the systems I was required to implement, but we'll obviously change details to both make it easier to see my point and obviously to make sure I don't do any copyright naughtiness. The example I'm going to be using is a CRM system, sometimes called CX or customer experience. I suppose because it sounds more high-tech to include an X in the name, I'm not quite sure why. But let's just simply call it CRM or Customer Relationship Management System because that's probably a more appropriate name. CRM systems are often used by companies' sales forces to manage sales cycles. I need to be brutal here, and the point of CRM is to manage a specific revenue-generating sales cycle. It has nothing to do with making customers happy. In order to achieve success, you need to be able to manage the customer when they order your solution. And in the same ways that McDonald's always wants to sell you fries with your burger, you have to try and increase the customer's wallet share. These applications assist you in this. I'm certainly not going to recommend any specific CRM system, and that's not really the point of this video. Each individual customer needs to make their own analysis to determine what's best for them. This just shows market share for those interested. It should be noted that if you look at CRM applications based on users or revenue, you'll get a very different view. This is because different CRM applications offer very different features and integration. In my example, I am using a rather complex enterprise-level CRM application architecture, as that's what I'm generally most familiar with. This shows you the CRM applications by software spend. Let's now look at the core elements of a CRM system in terms of managing a sales cycle. The first requirement is prospecting. At the simplest level, this is obtaining a list of customers. Depending on your CRM application, you may need to add the basic customer details here, as you wish to keep track of your attempt to address these prospects or customers. As a prospect is a low probability opportunity at this point, the amount of information required here is generally rather low. The next stage is you need to make contact with your customer, and this needs to be tracked. At the basic level, a schedule of customers you're going to call is required. At worst, this is a cold call. At best, you already have a relationship here. As you go through these steps, you'll be adding more and more information about the customer into the system. Now we have two rather separate systems at this point. The customer database, which we've discussed to a large extent, and an application which allows you to schedule calls and record the results. These can be separate systems, as this is not a mission-critical application and a single person is the only user of the data, or it can be integrated. It generally tends to be rather separate. The next stage is qualification. This requires a lot more interaction with the customer and requires a significant amount of research. All this data goes into the customer database, and any scheduling application, if you need to schedule meetings with the customer or even schedule meetings with other people to gain additional information about the customer. Two applications here, customer database and a scheduling application. This step requires even more interaction with the customer as well as involving other resources from your own organization in order to assist. All this data goes into the customer database, and any scheduling application, if you need to schedule meetings with the customers or schedule additional resources to become involved in your attempts to nurture your prospect. Now we come to the present your offer. This step requires also more interaction with the customer as well as involving yet more resources from your organization to assist, specifically with presentations or demonstrations. A key application which is also required here is a price list application. We now get our third application, as well as presenting your offer. As presenting your offer will require some level of pricing, and you need to have some kind of pricing system to gain that. All this data goes into the customer database and any scheduling application, and of course you're accessing a pricing application which is within your own organization. After you've presented your offer, you're always going to have objections and questions, etc. This step also requires more interaction with the customer, as well as involving yet more resources, or even the same resources that were involved previously, from your organisation to assist, specifically with gaining technical assistance in answering any questions or to renegotiate pricing. All this data, yet again, goes into the customer database and any scheduling application appropriately. And now we come to the final stage, which is the closing stage, and this requires yet more new systems, such as a purchasing or invoicing system. All this data, yet again, goes in the customer database and in scheduling applications, and of course you're accessing additional systems within your organisation to actually raise the invoices and do the purchasing and ordering. I must bring up at this point that the stages of a sales cycle, or naming, can vary a great deal. In fact, I feel that it's similar to the great religious discussions of the 10th to 15th century in Europe, and can be rather emotional for some people. Having experienced these great sales cycle schisms in my previous roles, I always get surprised how emotional people can get on the topic of the exact label to place in this particular stage or the number of stage. In this case, I simply picked a typical sales cycle from the internet, and I must admit this is not the same as the last sales cycle steps I had to deal with. If you actually think through this extremely carefully, back to my CRM application, that you could actually perform most of this on a spreadsheet. And I have to admit, in my early career, that's exactly what I did, and I'm sure most sales reps did. I'm sure if I was John Tiel and managed to go back into time to see how the Salesforce managed sales cycles today, I would be rather shocked. However, John Tiel was only interested in retrieving an IBM 5100 so he could save the world from a nuclear holocaust, which it seems he was successful in doing so. However, this simple single-user approach using a spreadsheet or even a pad and paper has a number of major issues. The first was management oversight, or lack thereof. A sales rep was normally a part of a team who reported to a manager, who in turn needed to provide forecasts to their management layer above. The manager needed a system which allowed him to merge all the activity of his subordinate sales reps into a single view, and a dozen spreadsheets was simply not going to cut it. However, on a side note, back in the day, each rep would provide a report to the sales manager's admin, who then consolidated it manually into a single report. However, these days, few sales managers have the luxury of having an admin sigh. The next issue to overcome was what occurs when the sales rep goes on holiday, or worse yet, leaves the company. A replacement would have to recreate all the work the previous rep had done, as well as gone through the paper trail to work out what was happening with the current sales cycle. You need a system which archives all the prior activity so others can use it in the future in case holidays or people resigning impacts your sales cycle. This also has some interesting additional benefit. If you can actually leverage past work, you can use that to assist with new sales cycle. The amount of data collected in the sales cycle is significant, and if stored and archived correctly, this can be used in the creation of new sales cycles. Thus, the modern CRM system was born. This was still a single image core application with separate systems running the client applications at most. So we've not yet fully moved into a distributed computing architecture yet. It's true using something like the old Oracle RAC would allow you to distribute your database at least, but to do this in a robust manner you still need high-speed interconnect and big servers. Thus, initially, the CRM systems were primarily focused on duplicating the old spreadsheet methodology. This solved the reporting, replacement, and archiving issues I've mentioned, but it did not take long for CRM providers to realize the CRM system could provide direct assistance in the sales process, as well as simply reporting and archiving information and scheduling. For example, in the prospecting stage, we could now leverage other systems which provide information about, let's say, installed base, industry information about the customers from accounting systems, information available in the public domain, and so on. There are a lot of additional systems which could be leveraged, and while initially this was done in a very manual and clumsy manner, the final endpoint was utilizing the strengths of a distributed architecture by integrating all this into a single screen. Now, of course, you could actually extract all this external sources of information and place it within your main CRM system. But this made no sense, and it was easier to create a SOA-like layer, or even at the interface end, to bring all this information on a single screen. Each source of information could reside in its own separate OS image. Presto, distributed computing was the answer here. You can even distribute your system even more than this, particularly the data, especially if the data was only read-only. You would not want your core accounting systems to be loaded down with unnecessary work from the reps as they extract information from it. So copy the relevant information into a read-only environment. And if you're using cheap commodity servers, you can actually do this and do it as many times as you need. Modern databases allow you to copy this information in a seamless manner with minimal, if no, impact to the performance of your core system. And using commodity servers allow you to scale up or down or left or whatever as much as you require. Provisioning software allows you to quickly create an environment if you so need to immediately, or to close it down and use it elsewhere if you so desire. There are of course some issues with this distributed architecture, as this kind of architecture was reasonably inefficient. However, this was negated by the very low cost of commodity servers. Even if you're paying 5k for a 1U rack-mounted server, 10 of them are still a lot cheaper than a single 100k enterprise class server. From a CPU compute point of view, it was incredibly inefficient, but from a cost point of view, it was cheaper, and that's what really counted. Cheapness. There were other problems which did increase the cost, and that is you need a lot of administration, management and provisioning software, unless of course you had a horde of administrators and operators, which is not really what's going to ever occur. However, depending on the scale of your commodity server farm, it still is economically viable. There are also other technical issues, such as such a distributed system lacks deterministic behavior. One minute when you're looking at a customer service history, everything is working wonderfully. The next time you do so, you connect to an overloaded server or a server which is having technical issues, and guess what? It doesn't work particularly well. I fondly remember software problems taking hours to cascade through a server farm before enough people noticed it to report the issue. In most cases, the easiest solution was to reset hundreds of servers rather than to do a root cause analysis and eliminate the cause from the beginning. As long as the system was not mission critical, where downtime really cost real accountable money, there's no issue to the company. However, I must admit that even when a non-critical system went down for a while, it did cause a lot of people to sit around twiddling their thumbs. This may not have been a measurable accounting impact, but was one in a non-measurable manner. But then, as long as your distributed system was cheap enough, this possibly was acceptable to the company. In conclusion, the advent of a distributed computing using commodity servers has resulted in an explosion of new use cases which assist businesses and users at a price point which makes them economically viable. It's no wonder this segment of computing has exploded, as it was an underdeveloped segment which has only really expanded in the last 10 plus years when the whole distributed computing environment or architecture became viable. I personally think that we're about here in the adoption of this technical architecture or this distributed architecture, although this is only my own subjective wild guess. Now we come to the crux of the issue. Has the distributed computing architecture replaced the big box model of computing? The answer is some non-appropriate applications have moved from the big box with a one or a few tightly integrated OS images to a distributed architecture. This is absolutely the case. But those applications which are considered as mission critical have generally not moved to a distributed architecture, at least yet. There are a host of reasons for this, but one of the key ones is some applications cannot be broken up into isolated components, especially if data needs to be updated. While it's true servers such as the Oracle Exadata is made up of a number of separate servers, they are all connected together with a very high-speed, low-latency interface. This way, when a record is written, this can be quickly and seamlessly synchronized across all the separate servers without impacting the overall performance of your database. You could do this with a low speed and a high latency interconnect, but then you have major performance issues and the whole architecture just simply does not work. Thus, some applications have to run in a single OS images, and if they do connect with someone else, they need a high-speed, low-latency interconnect to other OS images. These are typical core applications such as core banking GL or general ledger applications, core billing systems in telcos, core insurance payment and claims systems, etc. These are very mature and stable applications which normally reside in very large companies. This segment may not be growing rapidly like the distributed computing sector, but is nonetheless reasonably large, critical, and is stable. Thus, for the end of the video, we can see that the distributed computing architecture using commodity servers filled a new market segment, and due to its cost effectiveness, this grew very rapidly indeed. It did absorb these types of distributed applications which were previously hosted on big boxes, but those applications were always niched due to the high cost of deploying them on such a high cost, even if highly reliable, server architecture. This growth has been explosive, which has allowed hither unknown application types to provide benefits for businesses and customers. I'm uncertain when this segment growth will slow, as it does seem to have some legs left at the present moment. This architecture finds it, on the other hand, difficult to replace the older big box architectures applications in larger companies. It's possible, but it's not optimal and can make little economic sense. Thus, it's generally not done. And so, sadly, we come to the end of my part 2 of my video on Information Technology Thought series. In this case, looking at the advantages and disadvantages of a distributed computing architecture using commodity servers. Alle guten Dinge kommen zu einem Ende.